Can you see my screen?
Yes.
Okay. So thanks for Max for the introduction. Today I would like to basically discuss how to compute different properties of metal alloys with neural network potentials. Here I won't focus on any aspects of what is neural network potential, as I assume that previous speakers already covered this topic. I will be following mostly my latest paper, which is quite pedagogical, and discussing how to compute properties at finite temperatures. And we present there a machine learning framework to take into account different degrees of freedom at temperatures from cryogenic to nearly melting point. So let's start. Why bother at all? So for example, if we look at the heat capacity of nickel, we see that it looks nothing like idealized system, that there are some quantum, we can see the effects of quantum excitations at low temperatures. Then there is the peak due to the magnetic excitation, and at high temperatures there is the electronic excitation, and the classical limit is completely off. And so how do we treat this? What do we do in this kind of situation? So here we propose a machine learning model, which is combination of a neural network and a model which predicts the electron density, the density of it predicts dose of electrons, and this helps to cut a lot on computational time and predict the properties accurately at high temperatures. As I mentioned before, I will mostly focus on their calculations and won't talk about the neural network. But if you're interested in more details, you can check out our paper. Also, so here we basically trained a neural network which is followed a Beller-Parnell approach. We use symmetry functions as the descriptors, and that's how we built our data set. So our data set contained around 2,500 structures. The 10% of those we used for testing. We were building the data set iteratively, and in the end it contained bulk, liquid, interfacial structures, free surfaces, crystal defects, and so on. All the forces and energies we computed with code quantum espresso, and we used to perform all the calculations with spin polarized DFT. So as you know, a nickel below Curie temperature is ferromagnetic, and why we decided to stick to non-spin polarized calculations is because if you look at the equation of state at 0 Kelvin, the ground state, their equilibrium lattice parameter doesn't vary that much. So, but of course, it will affect maybe the lattice expansion coefficient, thermal expansion coefficient, or other thermodynamic observables, but including the taking into account different spin configurations comes with a huge difficulties for neural network, because for every ionic configuration you would need to include also several spin configurations. So this has been done, for example, for iron, but then the basically the outputting predicting energy was averaged energy over different spin configurations, and it was done in a narrower temperature diapason. So here, as I said, we were expanding our data set iteratively. We started at first with several trajectories generated by replica exchange molecular dynamics. So we used these sampling techniques to diversify our data set, and then out of those we selected with FPS 1000 the most diverse points. So that helped us to train our first neural network model, which already was not failing in some picoseconds. And then we were computing more structures, so using that first potential, and including the structures which were difficult to predict with neural network back. So and improving our model, also including structures which were interesting for our purposes. So as you can see at the learning curve on the left for the neural network we trained, there is still some potential for improving accuracy by adding more data. But the accuracy which we reached with the current data set, it was basically already close to the accuracy of the potential. And further, I will show you the observables which we used for validation, and the neural network potential was able to predict those properties at high accuracy. So here you can see that here we benchmark neural network potential against EM. In EM was this particular EM was pretty good. It was developed by Mission and improved several times. So it was mostly trained to predict high temperature regimes, but also they were including into the training, they were including not only the energies and forces of the structures, but also some the values of properties to tune the EM to predict these properties better, while a neural network is completely general and trained only on DFT energies and forces. So, and as we can see here, for example, at the curves for phonons, at the phonon dispersion curves, neural network predicts quite close to the experimental values or the curves compared to EM. So, and phonon dispersion, the dispersion curves were computed with finite difference method, meaning that it requires to predict quite well small lattice distortions to reproduce the phonon curves accurately. And neural network does it well. So another property we used to benchmark our potential was generalized stacking fault. Here we can see that both EM and neural network, they predict quite close to DFT calculations. So here neural network was trained on these points, and they were included into the training set, also the points of the relaxation. So the stacking fault was computed by changing the vectors of periodic boundary conditions, and by that introducing a slide between two planes through periodic boundary conditions. So another important property is rigid surface separation. Here we can see that both neural network and EM, they reproduce the level of stability quite well, but EM shows some weird unphysical behavior for the separation curves. Similarly, similar behavior was observed, for example, for EM potential for aluminum magnesium silicon potential. This can be linked to the fact that in the end EM has its some sort of functions fitted to recreate the potential energy surface. While here we see continuous continuous behavior of the curve computed with neural network, and that it reproduces well the data was trained on. So with this, we come to the finite temperature properties. So before, it was quite easy to verify the behavior, our potential, because we could relatively easily compute pretty much everything with DFT at low cost. While the problem with finite temperature is the temperature properties, that you need to then you need to run longer simulation to converge results, or you need larger cells, and this is already quite difficult to compute with DFT methods. One can run, of course, ab initio MD, but then it's computationally expensive. And here the neural network potential steps in and helps you to reduce the computational time and compute these properties with high accuracy. So here first we show the bulk properties. So as the debye point for nickel, or temperature for nickel, is around 400 Kelvin, we expected to see the influence of some quantum nuclear effects. So that's why at low temperatures we ran path integral molecular dynamic simulations. But as we can see here, these effects are not that well pronounced. There is more influence by magnetic transition, by magnetic degrees of freedom. But in this case, we don't take them into account. But at high temperatures, we can see that the neural network potential reproduces well the experimental values, because we also had structures corresponding to liquid structures, while EM, although it also was trained to reproduce high temperatures, is much more off in comparison to neural network. Sorry, the EM, it had some for example, melting point included into the fitting, but it was fitted to the low temperature structures, while a neural network was fitted in the whole diapason of temperatures. So here we come to the heat capacity. So as we've seen before, heat capacity is quite tricky property to compute. And if we, for example, look at the purple curve, dash curve. This is the calculation performed in classical terms only for ions. And we see here that it doesn't capture the behavior at low temperatures, where we need to take into account quantum effects. And it's off by almost 20% in comparison to experimental data. So what we have done here is we again ran path integral molecular dynamics at low temperature. And we can see that now it describes perfectly the experimental curve. And at high temperatures here, we used another machine learning model to predict the electron density of states and to compute the contribution comes from electronic degrees of freedom and complement our model. So typically, what people could do, they could run, for example, additional calculator ab initio MD to compute this contribution, while we took the data which was already available. Basically, we learned the density of states for the data set we generated to train the neural network. And then we predicted the density of states at every point where we calculated heat capacity for every trajectory at fixed temperature. And then we corrected the value at every point by this contribution. So as a result, we got a full description of the heat capacity within the whole temperature range. Another important property is free energy of defects. Previously, in the validation part, I showed that we computed the single vacancy and interstitials at the ground state. But in fact, these values are not very telling, as these parameters, they come as input entries in macroscopic models for some where you want to model the behavior at higher temperatures, and there you want to know what is the free energy of defects at that temperature, and you can see that it varies by your 0.4 almost 0.4 electron volt, which is quite a lot. And what people could use, for example, thermodynamic integration to take into account this free energy contribution due to at high temperatures. And in this case, we use the neural network as a proxy to compute this contribution. And while previously, usually people use they performed the integration using the free the potential energy surface from the ab initio calculations, which is again more expensive. And here we can see that we're with neural network, we nailed the experimental data. While EM potential, for example, if we use that, it underestimates the contribution at high temperatures. So also we computed we proved that it's possible to compute with neural network potential properties of melt as self-diffusion coefficients and viscosity. And it gives you similar statistical uncertainty associated to EM potential. And these calculations, they require a quite longer convergence time to get accurate results, but it's still manageable within a reasonable time. So one could also compute these properties as well. And last but not least is solid liquid interface properties. So both melting point and interface free energy we computed with coupling lamps and their another software plumed, where you can perform metadynamics and umbrella sampling. So why this is important? Because, for example, interface-free energy is a highly anisotropic property. It's very difficult to compute it, to extract this property experimentally. And in simulations, it also requires large large simulation cells. So you can't really compute these properties with DFT, while it's still affordable with neural network potential. And as we showed before, that you can compute the properties with quite high accuracy with this potential, which gives us a hope that this can be a complementary tool to direct experiments or to complement the understanding of interfacial properties. With respect to melting point here, I would like to mention that while EAM it also contained in its fitting explicitly the value for the melting point. Here, the neural network we trained only on we didn't include any macroscopic properties, and it's still within 2% in comparison to experimental value, so which is also quite accurate. So thank you for your attention, and this is the take-home message that maybe neural networks are not very good for cats, but they're quite good for nickel. So thank you.
That's terrifying, but thank you. Well,
so how do we thanks how do we proceed? First I will answer the questions about the talk, or we go to tutorial and then all the questions.
Let's see if we have questions. So anyone who does have a question, please raise your hand now. I already see a hand. 2 hands, in fact, 3. All right. I think I saw Peter first, so.
Yes, thank you very much for the presentation. So I have a question about, for the metals, a lot of properties are determined by defects and extended defects. So I'm interested in things like dislocation. So the question is, do you plan to extend your training with more defects? And the second part of the question is, so I was pretty convinced with your explanation that you can get away with non-spin polarized calculations for the bulk properties, but do you think the same arguments will hold for defects as well? This is my question.
Okay, so your first question is if you can compute dislocations with this potential, and if their defects properties are affected by the fact that we use non-spin polarized calculations, right?
Yes.
So dislocations, so I think as far as I'm concerned, the dislocations they are predefined by the competition between FCC and HCP phases. So basically, it means that if we can capture these phase stabilities accurately, then I would expect that you can compute dislocations as well. Also, all these files are available, and for example, if you so what's actually the size you need to compute dislocations? I think it should be pretty large, right?
Yes, it's
So
for sure.
So I think that yeah, I think that it would be possible. But
are you interested yourself with your project, your work in dislocations at all?
I would say that for the moment we're not planning any further extensions towards this direction. Yeah, but in principle, I think in the tutorial I have a link to the materials cloud where you can basically find all the files to run this neural network, and also you can extend it with your data and retrain the weights using the same symmetry functions, and you can see if that improves your calculations. About non-spin polarized calculations, I would say that if you run it at the high temperatures, then unlikely, because their nuclear is paramagnetic. But at low temperatures, so far for two-dimensional defects, we saw quite good agreement, but well, I haven't run it myself, so I would say that I think that should give you at least a fair estimation of what it should be. Well, in any case, running non-spin polar, including any sort of magnetic effects, especially for such a large simulations, it would be a lot of pain, I think, because like you can't run directly DFT for sure, and
yeah, I mean it's a difficult question. I just wanted to know your feeling about it. So thank you very much.
Thank you for the question.
All right, we have, let's see, we have a few more raised hands. Natasha, how long is your tutorial?
How do I estimate that? Okay, average.
Let's try two more quick questions, but quick, okay? So, Jeonbum, you first, or?
Oh, I will ask her later. Yeah, maybe.
Okay.
Yeah, thanks.
Then Victor.
I have a question that can potentially be quick. Thank you very much for the talk to begin with. So I see you predict with your neural network potential a lot of measurables, which is nice. And I was wondering if there are at this point any measurables that you would like to predict that you're not able to with this potential, and what the potential reason could be for that.
Any measurables which I would like to predict with this potential, but I can't. So what is the limit of the potential, basically?
Yes, exactly.
There is no limit to it. Well, I would say that something which would require even larger cells than what we had. What could that be? Doesn't come up to my mind at the moment. Maybe I will think and let you know if.
Okay.
There is one thing. There is one thing if you go back one or two slides.
Yeah.
The heat capacity curve. You said you don't include the magnetic effects, right?
Yeah.
I mean, see a way that you might be able to include in the future?
Well,
I think Ivan was also saying he was working on magnetic materials,
So, okay, so in future, what we want to do, because like now I also work on multi-component alloys, which also have some magnetic contribution. What we want to do, basically, we want to treat magnetism as another species, and by that, so basically, let's say you have nickel up and nickel down spin, and then these are two different elements, and then you have an alloy of two elemental nickel, let's say, and by that you would treat magnetism. So maybe I would look. So I think we will look into this direction, and I don't know if we will go back to nickel, but in general, maybe that would be part of my current project. Yes.
Okay. Berik, you also have your hand up? Do you have a question?
Yes, I have a question about actually this heat capacity calculation. Did you calculate the? By the way, thank you. It was a great talk. Did you calculate the heat capacity for EAM?
Yes. Yes.
Sorry if I missed it.
Yes, sorry. So basically, the reason why you don't see it, because it almost coincides. It's a very valid question, but yeah, so it almost coincides here with the neural network ion contribution.
First one, classic one.
The purple one.
Purple one.
Yes.
Okay.
So and sorry, if you in the paper we show it as well. So we actually say it in words that here you don't see it because it's almost identical, so we don't plot it. But in the tutorial, we will compute the heat capacity for EAM actually from the raw data. So you will see that it's almost the same. Yeah.
Okay. Why there's no curves or calculations between 0 and 100 Kelvin? Is that?
But there is no calculation between 0 and 100 Kelvin.
Low temperature?
Because it's more difficult to convert PMD simulations, and I think we just started from 100 temperature because of that. Because, yeah,
okay.
Because it was just high uncertainty, we just didn't include that.
But you can calculate with EAM. There are methods to calculate this curve. It's the highest contribution is from vibrational.
Well, I mean, in this limit, it's maybe if you're interested, like in this narrow limit, maybe it's easier to compute harmonic heat capacity.
Yeah,
will be much cheaper, much easier, and as from 0 as you want. So
lower temperatures, there will be more electronic effects actually. So that's why my question, why there was
lower temperature, more
at lower temperatures, the electronic effects will be different in the back. Well, there is this magnetic curve. You have this shift. That's the magnetic part. But in the lower temperature,
at the lower temperature, there is almost no electronic contribution.
Okay.
Yeah, so the electronic contribution on this plot, you can see it would be basically the difference between the yellow and purple curve. This is the difference due to electronic contribution. And at 0 Kelvin, the difference is almost 0. Due to electrons, but there is a difference because, so the difference due to quantum excitations is the difference between dashed purple line and experimental points, or like purple triangles as you want.
Okay, thank you.
Thank you for the question.
All right, this sounds like a good point to go to the tutorial where we actually compute this thing, as you said. So
yes, okay. So how do we do this tutorial? I don't have to share the screen. Is that how is that right? So I just show my camera and then everyone can see the deep note, right?
Yeah, I mean, there is some benefit to you running the notebook for us. And
no, so I should share. You mean that I should share the screen? It's better if I share the screen, you mean?
I think so, yes.
Okay, then just one sec, I will. Oh my God, what did I do? Sorry, I closed my Chrome by mistake. So there is this funky thing is that I need to reinstall lamps every time I run the notebook. So sorry, maybe I could take one quick question. Meanwhile, let me see if I need to reinstall it actually, or it just runs smoothly. It's a bit moody. Yeah, I don't know how it's stuck.
I'm going to try to duplicate it.
Uh-oh.
So the lines prefixed with an exclamation point are reinstalling lamps.
No, don't install it for now.
Okay.
Let me first see if it works. Okay, it doesn't work, so I need to install lamps. Okay, while it's installing, maybe I could take one more question if anyone had a...
It seems like the module lamps is not installed. Yeah.
Yeah, I don't know why it was like, I think some dependencies they crash when the notebook freezes. So it was basically, it was 2 times when overnight it stops working without any modification. Okay, the lamps is almost installed. Okay, maybe I will shortly tell what are we gonna do here. So, and I want to share my screen with you. That's also true. Okay. Can you see my screen? Okay, very good. So what here I would like to show is basically some of the properties which I presented could be computed in a Python notebook. For that you need the ASC, and we will use lamps as a calculator. So why it's cool? Because you can use through lamps you can use different kinds of potentials which are available in lamps. So we will not compute the properties directly with the neural network potential. Today we will use EAM, which I used for benchmarks. So for the reason that you need to additionally patch lamps with N2P2, which is the software for neural network potential. And but basically I will also leave the parts which are needed to make this slight modification, and which would allow you to repeat the same exercise also with neural network potential. So here quickly I described, not very detailed, what would you need to do if you run it. Would you run it from scratch? Basically you install lamps, then AC, and then you hope that they find each other. For that you need to define expert Python path and library path variables. You need to also define the lamps running command, which AC will use to run your simulations, and so then it's done. So here by this link you can find raw files for neural network potential for Nikit, which I used. We saw some examples how to feed it, and with some input files for lamps for other properties. So first we import all the functions we need we would use later here as well. So here what I define the lattice parameters for the 2 potentials. Now we will use only EAM. Throughout the tutorial, some units conversions, and this already where we start the definition of our potential. So this part, this list of strings will be passed later to AC to tell to AC LAMS calculator to tell it which potential you want to use. So in this, the syntax is identical to as you would have written it in LAMS. So here we say that it's going to be pair style EM alloy. These are going to be the pair coefficients. So files are here. Indeed, we can find the EM potential we're going to use. And this is the dump file where you will dump your trajectory, but in fact, nothing will appear there. It's but because but it should be here, otherwise it might crash. So yeah, also so here I define the different equations of state, because we first start with fitting computing bulk modules for nickel. Here just the definition of different equations of state. We're gonna use this one, Birchmer-Nigon, and so let's start with computing reference bulk energy. So as a lattice constant, we take the equilibrium lattice constant for EM, which I computed before by minimizing the ideal FCC lattice at 0 Kelvin. And let's look what's written here. So atoms, so this line creates a slab, so it creates a cube of FCC lattice. The direction of this cube are these, but you can also create different orientations. This is useful if you want to create different surfaces. In fact, you can also use AC to compute the surface separation for different orientations, as I showed you in my slides. So this means that through PBC will be replicated only. So you will have basically your cube will be 1 times 1 times 1 across every direction that we're gonna work with nickel as an element. For now, it doesn't matter that much, but for some internal calculators which are implemented in EAC, this tells to the calculator which potential to use. This means that we use the periodic boundary conditions across every direction, lattice constant, which we defined above, and
so Natasha, I think it's working. Was it not working until now?
Yeah, it wasn't working.
Yeah,
but
I don't know. There's
but
something special about your notebook, but
I
yeah,
just reinstalled LAMS and it was working. Thanks, Venkat, for reinstalling LAMS is the clue to solution to all your problems. Always.
So so for some reason it always works for me, but whenever Natasha has tried, all I've done is try to recompile LAMS and it ends up working. So
are you saying that I'm the cause of my problems?
No, I'm not saying that. I'm just saying that if other people have problems, just try to recompile LAMS in the first cell.
It's the Pauli problem.
I'm so sorry.
You know, when Wolfgang and Pauli walked into a room where experimental equipment was located, the equipment would break down immediately. So that's the Pauli effect. not the Pauli principle. The principle is the quantum states thing. But
okay, thanks, Venkat. Yeah, so basically with this we created a member of class atoms, and it has this and we can set to which is basically let's look at it. So if we just print out atoms, it will tell you that it has 4 nickel atoms, so all the periodic boundary conditions true. This is the cell, and already now it has the calculator attached. But so basically with this action, you attach LAMS calculator. Here you define ULAM's calculator. So here is the command to ULAM's calculator, which we defined here above. So it means that it will execute this command in labs. So well, let's see what else. So we can look at the positions of atoms. Positions. So these are the positions of atoms. Also, if you import the NGLU, you can also visualize it, but here I will not do it. You can look at the cell separately. So now, since we already computed the potential energy, we can look at the potential energy of this system. It's all in electron volts for the whole system, meaning that that would be energy for 4 atoms. So that would be energy per atom. And then if we want to look, we can also look at forces, for example, which would be in electron per angstrom. So these are the forces for every atom. Yeah, so, no. So this is the brief introduction to how the AC works. So now let's see if we can do something useful with that. So for example, we can try to get the same, we can try to get the equation of state. So it means that entry units are going to be electron volts in angstrom, and pressure units will be in GPa. And fitting function here, I will use Birch-Merningham. That's the initial guess for the fitting function. So what is happening here is that we compute with this step for cells of different sizes. We will be computing energies and volume for these structures. So here you see the similar code as we just looked at above, but here I just in a cycle I change the lattice constant, means that I will compress and expand my cell, and by that I will get the energies of different then basically I will get the energies which I will fit with the question to get their bulk modulus. So ta-da! So here in this cell, basically I just fit so I stored energies and volumes in these variables, and then I just convert them into units according into their proper units, which I want to get. And then I just feed this data with the Birch-Merningham equation. And so like that, I can get the bulk modulus, for example. In a similar manner, you can compute other lattice elastic constants. But you just need to apply your, basically you would need to introduce corresponding distortions to the lattice cell to recreate specific elastic tensors. So here we got 180 GPa for AM, which is what I showed you, which is the value which I the value I showed you for the EM potential, so consistent. So okay, now we will move to computing phonon frequencies, which you can also get with AEC using lumps as a calculator. So here we will define this function. What is this here? So what is happening here is we create a bulk again. Then here we define the phonon calculator. That will be the size of supercell for which will be computed the phonon modes. Don't put this number too small, because otherwise you will not take into account some of the modes. Here again, you see that we so that was to compute phonon modes, phonon curves for different potentials. That's why I pass here the comment to lamps from outside. But in principle, here it's going to be always for EM. Then it computes the phonon curves with a finite displacement method. So it will run the calculations to compute forces. Then it will read these forces to compute the compute the force matrix, and then it will take the path in brilliant zone along which you want to compute the curves, and will give you the energy levels. So let's try if it works. Okay, it works. That's very good. So here I will also load experimental data, which I preloaded before, and let's plot what we've got. So you see here the black dots, these are experimental values, and yellow, these are the values we computed just now for EAM. It's a bit off. If we were to compute with neural network, well, I showed there the results for neural network that it predicts it much closer to experiment than EAM.
Natasha, is there a way to use this notebook to run the NN potential?
If you patch your lamps with N2P2, then yes. So
I need to patch my lamps.
Yes, you need to patch. You need to install N2P2, or so you need to compile N2P2 as a also I think as a shared library. Then you need to add a package which is on N2P2. Maybe they already included in LAMP. So basically, you need to recompile LAMPs such that it also has the module for recognizing N2P2 format. It's not that difficult.
So it involves.
Please go in. Yeah.
It involves reinstalling lamps again. Okay.
I mean, of course, the other way is to I think many codes provide ASE calculators. So instead of using a LAMPS calculator, one could just use an ASE.
Yes, but
for a different.
Yes, there is, for example, DFTB calculators. Yeah, so you can do that.
Yeah, I think LibRascal has an ASE calculator, for instance. Yeah.
Yes, LibRascal is compatible with ASE, but LibRascal is not neural network. So if you want specifically
neural network. Are you saying
network,
that only neural network is machine learning?
Yes. No. I'm just saying that if you want to use N2P2 potential, I don't think there is much workaround. But just should we take a question, because I think we're almost out of time. Max, what do you think?
Yeah, let's take. It looks like Berk has one question, and then we can continue in the poster session.
Okay.
Hello, I just was running your tutorial. I found that this PIMT variable is not defined. Does anybody
which one?
Come across? Yeah, that one. There is the in the first loop, EAM1 H equals to NP V stack line. The first loop.
First loop.
Yes, one line below.
Sorry, yes.
PIN DH1, and what's that actually?
No, that's
not defined anywhere, I think.
Yeah.
I try to run
No,
your
that's
install into
EAM.
lamps again.
Yeah, that's EAM 1H.
Oh, okay.
Yeah.
What we loaded. Okay.
Thank you.
And just one more thing that did you try copper nickel EAM potentials available in lamps? In
Say
nickel
again.
part.
Which
Copper nickel
potential?
alloy EAM potential.
Copper nickel.
EAM nickel part only. There is a copper nickel EAM potential in lamps repository. Did you try nickel part? You said that the nickel EAM doesn't capture the phonons and the dispersion.
Yeah.
The other one will capture that one.
Okay, I understand.
Maybe
Well,
you would like to try. I'm just trying that one.
Well, we haven't tried any other. We haven't tried any other potentials for EAM potentials for nickel. So we were just we basically took the most cited nickel potential for the most cited EM potential for nickel, and we benchmarked to that. So.
Thanks.
Yeah, so basically I'll just quickly mention, so here there is also an example how to run minimization with EC. For example, you can compute this way the free energy formation for a vacancy, for a single vacancy by deleting one atom and relaxing the cell later. So later, and then you will get the formation energy at 0 Kelvin. And also the last part is computing the heat capacity. So here you load classical trajectories for lamps for high temperatures, for above the by temperatures, without including any, so it's not PMD trajectories. And here we use basically we look at the fluctuations of total energy to compute the heat capacity. With temperature, we look at the gradient. And then here you can see the comparison of the two curves. So here, the raw date, here there are points for PMD simulations which are loaded from the data file for neural network, and here the yellow points which you can compute in this notebook, and comparison to the experimental values. This is only for ions contribution, and for electrons contribution, if you're interested, again, you can go to the Materials Cloud link, and they also provided notebooks how to feed the density, electronic density of states from data we also posted there, and how to compute the free energy from their free energy contributions due to electrons, and then you can use similar trick to compute the heat capacity. Yeah, so with this, I think I should finish my part. Thanks, everyone.
Well, thank you, Natasha, for the very nice talk in the tutorial. Yeah, so now that we have everyone here, oh, looks like some people have dropped out. Well,